Our next section is 11.2, Properties of Power Series. The preceding section demonstrated that Taylor polynomials provide accurate approximations to many functions, and that in general the approximations improve as the degree of the polynomial increases. In this section, we take the next step and let the degree of the Taylor polynomials increase without bound to produce a power series. A good way to become familiar with power series is to return to the geometric series first encountered in section 10.3. Recall that for a fixed number r, the summation from 0 to infinity of r to the power of k equals 1 plus r squared, etc., which ultimately sums to 1 over the quantity of 1 minus r, provided the absolute value of r is less than 1. It's a small change to replace the real number r with the variable x, and in doing so the geometric series becomes a new representation of a familiar function. Here we have the same function, but instead of r we have x. This infinite series is a power series, and it is a representation of the function 1 over 1 minus x that is valid on the interval the absolute value of x is less than 1. In general, power series are used to represent familiar functions such as trigonometric, exponential, and logarithmic functions. They are also used to define new functions. For example, consider the function defined by g of x, which equals the summation from k equals 1 to infinity of negative 1 to the k times k all over the quantity of 4 to the power of k all times the quantity of x to the power of 2k. The term function is used advisedly because it's not yet clear whether this is actually a function. If so, is it continuous? Does it have a derivative? Judging by its graph here, shown to the right, it does appear to be an ordinary continuous and differentiable function on the interval negative 2 to 2, which is identified at the end of the chapter. In fact, power series satisfy the defining property of all functions. Specifically, for each input value of x, a power series has at most one output value. For this reason, we refer to power series as a function, although the domain, properties, and identity of the function may need to be discovered on each one. Let's look at some terminology as we move towards figuring out convergence. A power series has the general form, the summation from k equals 0 to infinity of c sub k times the quantity of x minus a all raised to the power of k, where a and c sub k are real numbers and x is a variable. The c sub k's are the coefficients of the power series, and a is the center of the power series. The set of values of x for which the series converges is its interval of convergence. The radius of convergence of the power series, denoted r, uppercase R, is the distance from the center of the series to the boundary of the interval of convergence. How do we determine the interval of convergence for a given power series? The presence of the term x to the power of k or x minus a to the power of k in a power suggests using the ratio or the root test to determine the values of x for which the series converges absolutely. As we saw by previous theorem 1019, if we determine the interval on which the series converges absolutely, we have a set of values for which the series converges. Theorem 11.3 spells out the ways in which a power series can converge. And if you want to see the proof, it is in Appendix A. A power series centered at A converges in one of three ways. The series converges absolutely for all x. It follows by Theorem 1019 that the series converges for all x in which the interval of convergence is negative infinity and infinity, and the radius of convergence is equal to infinity. There is a real number r greater than 0, such that the series converges absolutely and therefore converges for values of the absolute value of x minus a being less than the radius of convergence uppercase R, and diverges for the absolute value of x minus a, which are greater than uppercase R, or the radius of convergence. The series converges only at a, in which case the radius of convergence is r equals 0. So let's look at our first example. Find the radius and interval of convergence for each of the power series a, b, and c. For a, we have the summation from 0 to infinity of x to the power of k over k factorial. Here we can see that the center of the power series is 0 because we just have x, not x minus a. And the terms of the series are x to the k over k to the infinity. Due to the presence of the k factorial, we test the series for absolute convergent using the ratio test, as we can see here, right? When we simplify this, we get x to the k plus 1 over x to the k, which of course is just the absolute value of x. And then we get k factorial over k plus 1 factorial, which of course is just 1 over k plus 1. So as k goes to infinity, we see that this limit equals 0, okay? The comments here are, notice that in taking the limit as k goes to infinity, x is held fixed. Because r is 0 for all real numbers, the series converges absolutely for all x. No matter what x we put in there, it's going to go to 0, which implies that the series converges for all x. Therefore, the interval of convergence is negative infinity to infinity, and the radius of convergence equals infinity. Now let's look at part B. The summation from 0 to infinity of negative 1 to the power of k over x minus 2 to the power of k all over 4 to the power of k. Here we can use the root test. And when we take the kth root, applying the limit as k goes to infinity, this all simplifies to simply, well, negative 1 to the k of the k, and this is the absolute value, so that negative 1 term just disappears. It doesn't matter. We're not going to oscillate because it's the absolute value. And then when we take the kth root of something to the k power, we just get the base, so that we ended up with x minus 2 over the power of 4. In this case, rho depends on the value of x, and remember with the root test for absolute convergence, rho has to be less than 1, so x minus 2 over 4 has to be less than 1. This implies that x minus 2 is less than 4, and then solving that, we get that x minus 2 is between negative 4 and 4, or x is between negative 2 and 6. So we conclude that the series converges absolutely and therefore converges on the interval from negative 2 to 6, which means that the radius of convergence is 4, right? Because remember, a is equal to 2, so the difference between 2 and negative 2 is 4, and the difference between 2 and 6 is 4. Okay, so the radius of convergence is 4. And when x is outside of that, we have rho greater than 1. So the series diverges on these intervals. and the divergence test applies. However, notice that the root test does not give information about convergence at the endpoints, which are x equals -2 and 6. Because at these points, the root test results in rho equal 1. To test for convergence at the endpoints, we substitute each endpoint into the series and carry out separate tests. At x equals -1, the power series simplifies to just 4k over 4k, and we can see here it diverges by the divergence test. When we input x equals 6, the power series simplifies to -1 to the power of k times 4k over 4k, which just simplifies to -1 to the k, and this also diverges by the divergence test. Okay, so so we have the interval of convergence is -2 to 6, excluding the endpoints, and you can see that here in the diagram with open circles as far as the interval of convergence. Okay, I like these number lines. To me, they kind of make clear these kind of concepts of the radius of convergence and the interval of convergence. So let's look at our last example, C, the summation from k equals 1 to infinity of k factorial x to the k. Here again, we're going to use the ratio test, substituting in k plus 1 for k. And so we get the absolute value of k plus 1 factorial x to the k plus 1. Again, this is similar to before, where we'd have k plus 1 over factorial over k factorial, and x to the k plus 1 over x to the k. So this just simplifies into x and then into simply k plus 1, the absolute value of x. And again, similar to part A, that can come outside of the limit because there's no factor of k that's going to imply it. So as we apply the limit, as k goes to infinity of k plus 1, we see that that goes to infinity. So we see that r is greater than 1 for all x not equal to 0. So the series diverges from -infinity to 0 and 0 to infinity. Now why, the only way to satisfy r is less than 1 is to take x equals 0, in which case the power series has a value of 0, right? If we plug in 0 here, 0 times infinity is still 0. The interval of convergence of a power series consists of a single point x equals 0, and the radius is r equals 0. Okay. The radius of convergence is 0 because a is equal to 0 and r is equal to 0 because it's at that same point, so there is no distance between them. All right. So let's look at another example. So let's look at example 2. Use the ratio test to find the radius and interval of convergence of the summation from k equals 1 to infinity of x minus 2 to the power of k all over the square root of k. So hit pause now and try this one. We've just gone through 3 of these, and this is very similar, and it's telling you which test to use, the ratio test. So why don't you try to do this problem, and then when you're finished, come back and hit play. Okay? So we're going to use the ratio test here. So substituting in k plus 1 for all of the k's, we get this original limit to find r, the value of r. And remember, we're looking for values of r that are less than 1 for convergence, for absolute convergence. So again, the x minus 2 to the k plus 1 over the x minus 2 just gives us that absolute value of x minus 2. The square root of k plus 1 over the square root of k, that becomes k plus 1 over k. I'm sorry, got a complex fraction here. Remember, we have a fraction divided by a fraction, so we're going to be multiplying by its inverse. So the square root of k is in the numerator over the square root of k plus 1 in the denominator. We can combine the square roots, as you see here in step 2. And then when we apply the limit as k goes to infinity, the square root value equals 1. So we just equal x minus 2. Since the limit equals 1, the absolute value of x minus 2. So remember, the series converges absolutely for values of r such that r is less than 1. So then we calculated the absolute value of x minus 2 is less than 1, which of course gives us that x is between 1 and 3. And so again, since a is equal to 2 in the original problem, x minus a, we can see that the radius of convergence is 1, okay? Because we're going from between 1 and 3, all right? So we know that on intervals between, I'm sorry, I just went blank there, between 1 and 3, this series converges absolutely. Once we get outside of that, we can see that r is greater than 1, so it diverges. So this, again, like a similar problem before, leads us to figure out convergence or divergence at the endpoints. If we test the endpoints, plugging in x equals 1, we get 1 minus 2, which is negative 1 to the k, over the square root of k. This series converges by the alternating series test. The terms of the series decrease in magnitude and approach 0 as k goes to infinity. We can see that because the numerator is staying as positive or negative 1 and the denominator is getting larger, so the actual series is getting smaller. Substituting x equals 3, we have really a similar actually no, because this is an alternating series. We have 3 minus 1, which is 1 to the k, which of course is 1 over the square root of k, and this is of course the divergent p series. So we can conclude that the interval of convergence is between 1 and it's less than or equal to 1 and less than 3. And here again you can see it mapped out and distinguished on a simple number line. So your text has a nice step-by-step instructions for how to determine the radius and interval of convergence, like we just did in examples 1 and 2. Step 1, use the ratio test or the root test to find the interval a minus r, a plus r, on which the series converges absolutely. The radius of convergence for the series is r. Use the radius of convergence to find the interval of convergence. If r equals infinity, the interval of convergence is negative infinity to infinity. If r equals 0, the interval of convergence is the single point, x equals a. And if r is between 0 and infinity, the interval of convergence consists of the interval a minus r, a plus r, and possibly one of its endpoints. Determining whether this series converges at endpoints, x equals a minus r or x equals a plus r, amounts to analyzing the series, the summation of c sub k, negative r to the k, and the summation of c sub k, positive r to the k. So this is a good stopping point to take a break. We're about 20 minutes into the lecture. Assuming you've paused, it's even longer than that. But this is about a 40-minute lecture if you run it straight through. And with the problems here, and they're a bit complicated, I imagine you're taking a little bit longer. So this is about the midpoint and a good break in the material. So get up, walk around, or pause and come back another day and finish this up. Although the procedure just outlined in the previous slide can be applied to any power series, it is generally used when nothing is known about the series in question. As we learn shortly in theorems 11, 4, and 5, new power series can be built from known power series, and in these cases, other methods may be used to find the interval of convergence. A power series defines a function on its interval of convergence. When power series are combined algebraically, new functions are defined. The following theorem, stated without proof, gives three common ways to combine power series. Theorem 11.4. Suppose the power series c sub k x to the power of k and d sub k x to the power of k converge to f of x and g of x respectively on an interval I. Sum and difference. The power series, the summation of c of k plus or minus d sub k x to the power of k, converges to f of x plus or minus g of x on I. And this is this is a very intuitive theorem, and it's been pretty consistent throughout all of our calculus courses as far as integrals and derivatives. Multiplication by a power. Suppose m is an integer such that k plus m is greater than or equal to 0. For all terms of the power series x to the power of m, the summation of c sub k x to the power of k, well, this equals the summation of c sub k x to the power of k plus m. And this series converges to x to the power of m f of x for all x not equal to 0. In I, when x equals 0, the series converges to the limit as x goes to 0 of x to the m f of x. Okay? So here now we're multiplying by a power of m on x. And so again, it's very intuitive since we're just multiplying the original power series by this factor, then the series converges to that same multiple times the limit that we had to the original series. So both of these are pretty intuitive. It's what your brain would typically do in a logical way. Let's look at the third one, composition. If h of x equals b times x to the m, where m is a positive integer and b is a non-zero real number, the power series c sub k h of x of k converges to the composite function f of h of k for all x such that h of x is in I. Okay? So here what they're doing is a composite function where we have a function inside of a function. And notice that even though we have this the value of the original convergence, f of x, is just adjusted by the composite input function, which again kind of makes some intuitive sense. So you might want to pause here and look this over and go through it a little bit more, and make sure it's in your notes. So let's look at example 3, combining power series. Given the geometric series 1 over 1 minus x equals the summation from k equals 0 to infinity of x to the k, which equals 1 plus x squared plus x cubed, etc., for the absolute value of x is less than 1. Find the power series in the interval of convergence for the following functions. So on these, what we're trying to do is figuring out what's happening with the original series. And so for A, we can see that what's happening is we're multiplying the series times x to the 5th power. And this is an example of theorem 11.4, the second case, multiplication by a power. So when we multiply by x over a 5th, we can see that we're just multiplying the geometric series by x to the 5th, which gives us the summation from x to the 5th plus x to the 6th when we multiply each of these subsequent terms, as we see there. So what's happening here is that we now have a summation of x to the k plus 5, right? x to the fifth times x to the k is x to the k plus 5. This geometric series has a ratio which equals x and converges when the absolute value of r is equal to the absolute value of x, which is less than 1. And so the interval of convergence is the absolute value of x is less than 1. When we look at example B, we can see that what we've done here is this is a composite function. If the original function is f of x, notice that what we've done is we've substituted in 2x where there's an x, so we have f of 2x. So this is the third part of theorem 11.4. So 1 over 1 minus 2x gives us 1 plus 2x plus 2x squared. So again, notice what's happening here is wherever there's an x, it becomes 2x, etc. So what's happening here is that the summation, the new series, is the summation of 2x to the power of k. And again, it's just doing a composite function. This geometric series has a ratio of 2x and converges provided the absolute value of r equals the absolute value of 2x, which is less than 1. Or if we solve that, we get the absolute value of x is less than 1/2, and so the interval of convergence is the absolute value of x is less than 1/2. Finally, in the last series, what we see here we are again a composite function, right? Where before we had negative x, now we have negative x squared. Right? We had 1 minus x, now we have 1 plus x squared. So if this is f of x, this is f of negative x squared. Okay? And when I say that, I'm not talking about the quantity, parenthesis negative x, parenthesis squared. I'm talking about the opposite of x squared. Okay? So again, when we see this in long form, everywhere we have an x, we replace it with negative x squared. Simplifying this, we see that we get 1 minus x squared plus x to the fourth when we have an even exponent in the original function. So we have an alternating series here, so we can rewrite this as the summation of negative 1 to the k, x to the 2k. Okay. This geometric series has a ratio of r equals negative x squared and converges provided, again, that the absolute value of r equals the absolute value of negative x squared, which equals the absolute value of x squared, which is less than 1, or simply x is less than 1. Okay? There's a couple more exercises here that I think would be a good idea to do, and I believe that these examples are also walked through in other videos in your homework. Some properties of polynomials carry over to power series, but others don't. For example, a polynomial is defined for all values of x, whereas a power series is defined only on its interval of convergence. In general, the properties of polynomials carry over to power series when the power series is restricted to its interval of convergence. Pay attention to that. In general, the properties of polynomials carry over to power series when the power series is restricted to its interval of convergence. The following result illustrates this principle. Suppose that the power series c sub k, x minus a to the k, converges for the absolute value of x minus a is less than uppercase r, and defines a function on that interval. Excuse me. Then f is differentiable, which implies continuous, for x minus a is less than r, and f prime is found by differentiating the power series for f term by term. That is, f prime of x equals the summation of k times c to the power of c sub k, x minus a to the k minus 1 for x minus a is less than r. So notice we're just applying the power rule of a differential, bringing the k down in front. Okay? The indefinite integral of f is found by integrating the power series for f term by term. And so again, what we have here is the power rule for integrals. The integral of f of x dx equals x minus a to the k plus 1 all over k plus 1. Plus c, where x minus a is less than r, where c is an arbitrary constant, which we know from integration before. This says two things about differentiation and integration. First, the differentiated and integrated power series converge provided x belongs to the interior of the interval of convergence. But the theorem claims more than convergence. According to the theorem, the differentiated and integrated power series converge to the derivative and indefinite integrals of f respectively on the interior of the convergence. Let's use this theory to develop new power series. Example 4, differentiating and integrating power series. Consider the geometric series f of x equals 1 over 1 minus x, which is the summation from k equals 0 to infinity of x to the power of k, which equals 1 plus x squared, for the absolute value of x being less than 1. Differentiate this series term by term to find the power series for f prime and identify the function it represents. Do the same thing for b, integrate this series and identify the function it represents. So we're doing a couple of things here. These are pretty straightforward for integrals and derivatives when we look at the power series, but then figuring out kind of the summation expression of that, and also the derivative and integral of the functions are pretty easy. So this is pretty straightforward, but it's really about understanding how these pieces fit together. So let's look at A. So if we differentiate 1 over 1 minus x, this is 1 minus x to the negative 1, but also, so you could do the power series, but 1 over an argument, remember, is the natural log of that argument. Right? So f prime x equals 1 minus x to the power of negative 2. All right? So that's the function that the derivative of this series is going to represent. Now let's differentiate the power series term by term. So the derivative of 1 is 0, the derivative of x is 1, the derivative of x squared is 2x, etc., 3x squared, and you can see that, okay? So the derivative of this is equal to, when we look at the power series term by term, we can see this is can be defined as the summation of k plus 1 x to the power of k. Okay? When k is 0, we get 1 times x to the 0, or 1. When k is 1, we get 2 times x. When k, etc. So that's kind of the hard part, I think, is kind of following the formulas and then rewriting it in summation and just thinking about, okay, when k is 0, how do I get this? When k is 1, etc. For me, I tend to write a table, k 0, 1, 2, 3, and then the values so that I start seeing a pattern. All right. Therefore, in the interval x is less than k, f prime x equals 1 minus x to the negative 2 power, which is the function the derivative represents, equals the summation of k plus 1 x to the k. So here we have the series, here we have the functional values that they're both asking for in these problems. Okay? Remember that the series, the derivative of the series, only converges for the interval of convergence, for the values of x in the interval of convergence as well. In this case, substituting x equals plus or minus 1 into the new powers reveals that this series diverges at the endpoints. Okay, and the same thing here, as this is stating, the theorem we just looked at, 11.5, does not talk about the endpoints. It just talks about it will converge. If the series converges, the derivative and integral will converge within that interval of convergence. Okay? So now let's look at part B, and if we integrate, this is what I was saying before, I don't know what I was doing with derivative there. When we integrate 1 over 1 minus x, this of course gives us the natural log of x, but here the composite derivative of 1 minus x is negative 1, right? So we have negative natural log of 1 minus x as the integral of the function. So there's the functional value that we get for the integral of the original geometric series. When we integrate each part, notice that the integral of 1 is x. The integral of x to the power of 1 is 1/2 x squared, 1/3 x cubed, as we go on. Again, the challenge here is to figure out what is the summation. How do I rewrite this as a summation? And of course, c is the constant. When x is 0, the natural log of 1 is of course 1. I'm sorry, the natural log of 1 is 0, because anything to the 0 power equals 1. So the left side is equal to 0 when x equals 0, and since every term has x in it, the right side is going to be equal to 0 as well, as long as we have a constant value of integration that's also 0. Because the absolute value of x is less than 1, that means this is a value, the x is a fraction smaller than 1, then 1 minus that fraction will always be a positive number. So we can lose the absolute value on the left side. And so this is suggesting that we then multiply both sides by -1 so that we have a little bit cleaner functional value here of the integral, which is the natural log of 1 minus x, which would then equal -x minus x squared over 2, all of these terms becoming negative. And so this can be simplified to x to the power of k over k. Again, the idea here, and this is a toughie, is to find the pattern that's happening here. When k is 0, I get -x. Okay? So here I have x to the 0. I'm sorry, we go from k equals 1 to infinity, not k equals 0. I'm guessing that applies since we know when x equals 0, it equals 0, so there's not another term there, so we can start at 1. So we get, when k equals 1, we get x over 1. When k equals 2, x squared over 2. So yeah, I can see this pattern there. It's much smarter to start at 1 to infinity. It'd be very difficult. Then we'd have to do like a k plus 1 times, etc. So we get the natural log of 1 minus x, which is the integral of 1 over x, 1 over 1 minus x, and then here we have the accompanying series that represents that integral. Now 11.5, as we just noted in the last example, does not give any claim to the endpoints of the series, and here we're at -1 and 1. In this one, it says it's interesting to test the endpoints. When x equals 1, the series is a multiple of the divergent harmonic series, and when x equals -1, the series is the convergent alternating harmonic series that we saw in 10.6. So the interval of convergence actually includes the -1 endpoint, but excludes the 1 endpoint. Now, it didn't ask you to find that, it just asks you to find those integrals, and we know that the series converges at x equals -1. Theorem 11.5 guarantees convergence to the integral, but only within the interval of convergence, which would be between those 2 points, it does not include those endpoints as an axiom or as a law. Okay? So in all of these problems, we're going to use either, we're going to work with the known power series and use differentiation, integration, or another combination. Okay? So when you're looking at these and trying to figure out their functions and find the power series, think about the integral. So look up the integral for inverse tangent, look up the derivative for inverse tangent, and see if there's anything there that comes out as a pattern. And so the derivative of inverse tangent is 1 over 1 plus x squared. So the integral of that will equal back this original function. The integral of 1 over 1 plus x squared gives us inverse tangent plus, of course, the constant of integration. Well, if you look at example 3c we just did a few minutes ago, when we substituted in x squared for x in the geometric series 1 over 1 plus x, we got this series of terms here, 1 minus x squared plus x to the 4th, etc. So we can see that the integral of 1 plus x squared is equal to the integral of 1 minus x squared plus x to the 4th, etc. Okay, so this implies that the inverse tangent of x, this integral, which equals inverse tangent of x, equals this integral, which gives us x cubed over 3, x to the 5th over 5 plus c. When we substitute in x equals 0 and note the inverse tangent of 0 is 0, the two sides of the equations agree, provided we choose 0 for c. That makes this much more convenient, okay? So we can get rid of the c. But now we have to figure out the power series. And so, when a good idea is to look at the numbers and the exponents, etc. So notice when k equals 0, we just get an x term. When k equals 1, we get 3 in the denominator and 3 on the exponent. So how do I get an input of 1 to make it 3? Well, 2 times that, 2 times the input plus 1, 2k plus 1 will give us 3. And that works here when k is 2. 2 times 2 is 4 plus 1 is 5. So that's our pattern here. So we can see the denominator is 2k plus 1. The power is 2k plus 1. And then, as we saw before, it's alternating between negative and positive. So we know that factor negative 1 to the k. By theorem 11.5, this power series converges to tangent, inverse tangent of x for x less than 1. Testing the endpoint separately, we also find that it converges at x equals plus or minus 1. Therefore, the interval of convergence is inclusive, negative 1 to 1. Okay, so these are challenging, trying to figure out the patterns, etc., but looking at what you've done before and kind of holding those examples in mind. All right, so look at B, and we've got the natural log of 1 plus x over 1 minus x. And in just the last example, we saw the natural log of 1 minus x, right? This was in example 4. The natural log of 1 minus x equals negative x minus x squared over 2 minus x cubed over 3, etc. Okay? If we replace x with negative x, right, which is what we can do based upon theorem 11.4, composition, so then we can plug that in and we get 1 minus negative x, which of course is the natural log of 1 plus x. If we replace each of these x's with negative x, we get negative x positive, negative x squared is still positive, so this stays negative. Negative x cubed is negative becomes positive, and so we have this alternating series. But we're not done there, right? Because that's only giving us the natural log of 1 minus x, which is the denominator, and the natural log of 1 plus x, which is the numerator. But remember from the property of logs that when I take a log of a quotient, this is equal to the log of the numerator minus the log of the denominator. And again, by 10(4), when we have a sum or difference, we can take the derivative of those terms. So what we can do here is we can take the terms of the natural log of 1 plus x and subtract the terms of the natural log of 1 minus x, as we see here, okay? And so what ends up happening is everything becomes doubled. X minus a negative x, x squared, negative x squared minus a negative, that term disappears, and we're left with just the odd terms and what am I trying to say here? And a multiplier of 2. So again, looking at this, when k equals 0, we get x. We actually have the exact same thing we had before, except that it's not alternating. So we can put the 2 out in front, and then it's x to the 2k plus 1 over 2k plus 1. And again, what we're doing here to write it in series representation is looking at the values in the numerator, denominator, and on powers, and then trying to relate them to the integer values of k. K equals 0, k equals 1, etc. Okay? So this power series is the difference of two power series, both of which converge on the interval the absolute value of x is less than 1. Therefore, by theorem 11.4, the new series also converges on that same value. Okay? If you look carefully, every example in this section is ultimately based on the geometric series. Using this single series, we were able to develop power series for many other functions. Imagine what we could do with a few more basic power series. The following sections accomplishes precisely that.